Okay, so there's three more examples here in this section, three more that I want to look at, and then I'm going to start looking at some horizontal asymptotes as well. And so the first example, again, I'm looking to figure out when does this denominator equal zero, because having your denominator equal to zero is really the key in determining do you have a vertical asymptote or a hole. And then if the numerator is also zero, then you know that's a hole instead of the asymptote. But in this case, there's really no values that would equal zero, because if I try to set that equal to zero, I would get -9. And so I could get x is equal to plus or minus 3i, but we're only graphing in the real number system. So this particular function actually has no vertical asymptotes and no holes. Okay. And you might say, well, what about -3? Like x is equal to -3. Although that gives you 0 in the numerator, it gives you 18 in the denominator. And 0 divided by 18 is still 0. And so that doesn't give us an asymptote or a hole. What it actually does is, when your output or your y value is equal to 0, that actually gives you an intercept. So when x is 3 and the y value is 0, we actually know the x-intercept is equal to -3. So that's kind of a good segue or a good foreshadowing into more things that are coming. Now, let's look at the next example. And feel free to pause the video if you feel you understand this. Feel free to pause the video and work ahead and then check your solution. So the first thing I'm going to do is factor out the x on the top. So I get x plus 4. And if I factor the bottom, I'm noticing I have an x plus 4 times x minus 2. Now, so there's actually two things happening here. Clearly, x plus 4 cancels. When you can cross that out, when you can remove factors that would have given you 0 in the denominator, that's an indication that we have a hole. So I'm going to start keeping track of the hole. It happened when x was -4, right? Because remember, -4 would have been like the 0 over 0. Because if you're choosing x to be -4, you would have had 0 over 0. And so you're removing that. Anytime you can factor that out, that's a hole. And the value that makes it equal to 0, that will in fact be the x component of your hole. So then we have our reduced form. So let me write that. So the reduced form, the x stays, and we have x minus 2 in the reduced form. So what I'm going to do now is take that -4 that I had solved, and I'm going to put that into the x here and here. So then I'm going to get -4 over -4 minus 2. Which is -4 over -6, which is 2/3. So that is how I get the y component of the hole. I have to substitute the x component into the reduced form. Now, our reduced form still, so I'll call it our reduced form still has an issue, I should say, when it's x over x minus 2, it still has an issue of being 0 in the denominator, right? It still has an issue when x equals 2. When x equals 2, I get 2 over 0. This tells me I have a vertical asymptote. So this graph actually has both a hole and a vertical asymptote. How cool, right? And where does the vertical asymptote exist? When x is equal to 2, because that's still a denominator issue. So it has a vertical asymptote, and the equation of a vertical asymptote, which is a vertical line, is x equals 2. Okay, then we have one more example, and this last example here, it looks like there's lots of factoring happening. So what I might do is actually erase this for this next example. So I have a little bit more space. Hopefully you proportion space more appropriately. So this looks like it factors into x plus 6, x minus 5 in the numerator, and it looks like it's x minus 5 times x minus 5 again. So x minus 5 cancel. And so remember, when you can cancel something to get a reduced form, which is x plus 6 over x minus 5, that tells you that there's a hole. So your hole is at 5 because that's what was canceled out. And then we're going to put 5 into the reduced form. Now, some of you see where this is going. When you try to put 5 into the reduced form, you get 11 over 0. 11 over 0 doesn't exist. 11 over 0 is an undefined number, not an indeterminate form, and it's undefined. And you can't represent a whole with an unknown y value. So here's a weird anomaly. So because this whole actually exists on the vertical asymptote itself, right? Because we know we like if I tried to put over here, right? If I tried to put in 5, I would get 11 over 0, which tells me there's a vertical asymptote when x equals 5. So when x equals 5, I definitely have a vertical asymptote, but it also seems like I have a hole there, right, at x equals 5. Well, like a hole on a vertical asymptote doesn't really make sense. So it's like the vertical asymptote sort of trumps or takes over the characteristic. There's no longer a hole. So every once in a while, and you take a look, that's because we had a repeated root here of x minus 5. Oh, sorry. There's the bell. So every time that might happen, if you do have that repeated root, all that means is that, like, if there's still a 0 in the denominator without a 0 in the numerator, the vertical asymptote takes control. So this only has a vertical asymptote, and it's when x is equal to 5. The whole does not exist because the asymptote went right through it. So there's no y coordinate, which is kind of an interesting little thing. Okay, so that concludes the difference between how do you know if there's a vertical asymptote versus a hole. And again, it's all based on the denominator being 0, and is the numerator at the same time also 0. Okay, so next video, we'll talk about horizontal asymptotes.